What's up, guys? Welcome back. Patrick here. Moving on to the next indeterminate form that we're going to talk about. We're going to talk about indeterminate powers. And to do a quick little review of the types of forms we've talked about up until this point. So we talked about indeterminate quotients. And indeterminate quotients, they could be in the format plus or minus infinity over plus or minus infinity. Or they could be 0 over 0. And when we get limits in this kind of form, usually we try to apply LHospitals Rule, see if that simplifies the limit. It's not always going to simplify the limit, but usually questions you're going to get in this format will. And then indeterminate products are when you have plus or minus infinity times 0 or 0 times plus or minus infinity. And we did a bunch of examples on these types of forms. What we usually do with these is we take these and try to convert them to indeterminate quotients and then apply LHospitals Rule and see if it simplifies the limit for us. And then indeterminate differences, two formats, either positive infinity minus positive infinity or negative infinity minus negative infinity. So if it's in one of those formats, it's an indeterminate difference. And dealing with indeterminate differences is a little tricky in my opinion because there's a lot of different scenarios that you could run into. We showed how we can maybe convert the two expressions into one expression, getting a common denominator, and then it converts into an indeterminate quotient. We talked about how we can maybe rationalize certain limits, and then we also did a strategy where we factor out something from both of these expressions to create two separate expressions that are multiplying by each other, and then we use the properties of limits to simplify that overall limit, right? So indeterminate differences is a little bit tricky because there are multiple strategies and you got to be able to notice which strategy you're going to be working with. So the last form that we're going to deal with over the next couple of videos is indeterminate powers. Now you can spot these forms because what's going to happen is you're going to be taking the limit of a function that's in this format. You're going to have a function in the base and then a function in the exponent. So something like x to the power of x, for example. Right? You have a variable in the base and a variable in the exponent. It's kind of similar to certain functions we covered when we did logarithmic differentiation. If you remember, some functions there was a variable in the base, variable in the exponent. Actually, the process is going to be kind of similar to how we deal with limits when they're in indeterminate power form. So it's going to be in this format, and then more specifically, when you do a direct substitution, it's going to be one of three forms. It's either going to be 0 to the power of 0, it's going to be 1 to the power of infinity, or it's going to be infinity to the power of 0. Right? So one of these three forms here, then you know that you're dealing with an indeterminate power form. And we'll talk about how to deal with stuff that's in this form, but that's what you want to look for. So for example, if you got the limit as x approaches 0 from the positive side of x to the power of x, well, notice if we do a direct substitution, that's going to be 0 to the power of 0, which is going to be in this form over here. So you know that this here is an indeterminate power, and I'll show you the strategy on how to deal with that. So let's actually do that example. The limit as x approaches 0 from the positive side of x to the power of x. So as I mentioned, if you do a direct substitution, you'd end up with 0 to the power of 0, which is that first indeterminate form, indeterminate power form. And so we're going to have to come up with a different method to find this limit, and I'm actually going to show you two different ways to solve this. It's actually the same process. It's just one way. There's going to be a few extra steps, and the reason why I want to go over the longer way is because a lot of profs and a lot of textbooks show it the longer way. So I don't want you getting confused and thinking that it's a different process. It's actually the same process. It's just the longer way is going to have a couple of extra steps. So let's start off with the longer way. And what you want to do is you actually want to introduce another variable. So you want to let this x to the power of x equal y. Right? So y equals x to the power of x. And so if we let y equal x to the power of x, what we can do is we could actually rewrite this limit as the limit as x approaches 0 from the positive side of y. Right? Because we let y equal this, so we just subbed in a y there. And I'll come back to this limit over here in a little bit. What I first want to do is work with this, with y equaling x to the power of x. And what you want to do with this, very similar to logarithmic differentiation, is you want to ln both sides. And the reason why you want to ln both sides is because you want to take this exponent and you want to bring it down. Right? So you'd have ln y equals x times ln x. So y equals x to the power of x. We just change the format to this, ln y equaling x times ln x. And so what you want to do now is with this new format, you want to find the limit as x, you know what, I'll just write it here. You want to find the limit as x approaches 0 from the positive side of ln y. Okay, not just y, we'll do that in a little bit, but ln y. And ln y is equal to this, so this is basically the limit as x approaches 0 from the positive side of x times ln x. So let's just work with this limit for now. And notice that this is going to be an indeterminate product, right? Because if we do a direct substitution, this would be 0. And then what does ln x go towards as we approach 0, an x value of 0 from the positive side? Well, as we approach an x value of 0 from the positive side, notice that the function is going towards negative infinity. So this here would be negative infinity. So this limit is an indeterminate product. And as we know, to deal with an indeterminate product, what we do is we want to try to convert it to an indeterminate quotient. The way we do that is we take one of these functions, bring it to the denominator, get the reciprocal of it. The question is which one? I feel like x is going to be easier to work with. So if we got ln x over 1 over x, like that, right? Just took this x, brought it down to the denominator, and made it a reciprocal. So this is the exact same thing as this over here. And then notice that we know ln x, as x approaches 0 from the positive side, is going towards negative infinity. And then we know 1 over x is going towards positive infinity, right? As x approaches 0 from the positive side. So because it's in this indeterminate quotient form, we could apply LHospitals Rule on this. So this would be the limit as x approaches 0 from the positive side, ln x, the derivative of that is 1 over x. The derivative of 1 over x is negative 1 over x squared. So we'd end up with the limit as x approaches 0 from the positive side of 1 over x times negative x squared over 1, the reciprocal of this. One of those x's cancel out, so we end up with the limit as x approaches 0 from the positive side of negative x, which is equal to 0. Right? So this whole limit here, when we did the work, is equal to 0. And this process here, you should be fairly comfortable at this point with this process. We went over a lot of indeterminate product type of questions. So this limit here, the limit as x approaches 0 from the positive side of ln y is equal to 0. Right? So I'm going to write that result over here. Now, what's the problem here? The problem is we're not looking for the limit as x approaches 0 from the positive side of ln y. We're looking for the limit as x approaches 0 from the positive side of y, because we let y equal x to the power of x. So how can we take this and incorporate it here? Well, what you want to do is you want to use the property of, if you have some kind of expression here, this could be a variable, this could be a function, this could be whatever, a number. This expression is equal to e to the power of ln of that expression. Usually we go the other way. If you have something like this, that's equal to that. Or another format, popular format, is if you have something like that, it's equal to that exponent right there. Right? So usually we're going from this format to here, from this format to here. This format we're not going to be using, but what we're going to be doing now is actually taking this and converting it to that. And so if we use this property on the y is like the a. And so I'm going to convert this y to be e to the power of ln y. So we'll have the limit as x approaches 0 from the positive side of e to the power of ln y, like that. So this and this y and e to the power of ln y are the exact same thing. And the reason why we want to do that is because now we got this ln y that we could work with that we have right here. And so using the properties of limits on this, we can rewrite this as x approaches 0 from the positive side, or no, sorry. We would write e to the power of the limit as x approaches 0 from the positive side of ln y. Right? Use the properties of limits here. So if you got something like, let's say the limit as x approaches a of b to the power of g of x, like that, you can rewrite this as b to the power of the limit as x approaches a of that function in the exponent, right? That's a property of limits. So that's all I did. I applied that here. I kind of distributed that limit to the exponent. And we already know what this is. That's equal to 0. We already did all that work. And so basically, this ends up being e to the power of 0, which ends up being 1. And so that ends up being the final answer for this limit here. Right? So that's kind of the long way to do it. We introduce this new variable y, let this be equal to y, and then we worked with ln y, found that limit of ln y, and then we were able to convert this to that, distributed the limit, and then this limit we found over here, so we could just directly substitute that result. And then e to the power of 0 is 1. So that's the longer way to go about it. A lot of profs, a lot of textbooks will show this method. Personally, I don't really like this method. I'm going to show you a different one. But just in case you run into it, that's the way it's done. Now, the quicker way to do this, the way that I usually do these types of limits, is if we take that same limit, instead of introducing another variable y and then dealing with ln y, what I like to do is I still use that property where we have a, some kind of expression, equals e to the power of ln a. I just go to this step right away. So this a here would be whatever expression you're dealing with. In this case, it's x to the power of x. So we could rewrite this as e to the power of ln of x to the power of x, like that. And so that's what I do. I don't introduce another variable. I kind of just go right into this format, like that. I take whatever function we're working with, if it's in that indeterminate power form, and just convert it right away to this form, e to the power of ln of that function. And then what I do is I use the properties of limits that I did in that first example. So take that limit and put it in the exponent, ln of x to the power of x. And then what I do is I just take that limit in the exponent and rewrite it on the side and just work that limit through. So we would have the limit as x approaches 0 from the positive side of ln of x to the power of x. And then I just work this through, and then basically you could bring that exponent down here. So we'd have the limit as x approaches 0 from the positive side of x times ln x. It's that exact same process that we went through. This is going to be an indeterminate product. So we convert this to ln x over 1 over x, apply LHospitals Rule. So we'd end up with 1 over x, negative 1 over x squared. We know that that simplifies to negative x, and we know that that equals 0. We could do a direct substitution there, right? So that ends up equaling 0. So this limit ends up equaling 0, and then I just sub in e to the power of that result, which is equal to 1. Right? So again, it's the exact same process. It's just we don't bring in a new variable y and then deal with ln y. That could confuse some students. I feel like this is just a simpler way to go about it. Just take that function, convert it to this, use the properties of limits to take the limit here, put it in the exponent, and then just deal with this limit on the side separately. Right? So that's the way that I do it, but either way, it's the exact same process. The other way is just a couple of extra steps. But whichever way you do it, final answer is 1.